Hello. Dimensionality reduction is about pruning the number of variables in statistical and algorithmic models to the absolute essentials. This forms part of what is now called feature engineering. I'm going to take you through the why and how of this, and I'll do it in 4 easy stages. A quick look at the attributes of a good model, how to inspect the correlation structure of variables, carry out and interpret principal components analysis, and choose the reduced number of variables and how to prune them further when modeling. Some simple coding will be provided, and this will be in open source R. Of course, the same methods can be deployed in SPSS, Stata, or Python. Illustrated here are a number of different types of models, numerical, verbal, pictorial, that are representative of some phenomenon. Also is a list of attributes of good models. A key to good models is parsimony. That is, they incorporate no unnecessary variables or parameters and include no more than are necessary to do the job required. The more variables there are, the more time-consuming and expensive models are to build and deploy in production. Parsimony also helps models to be replicable and easily understandable. Good models should be beautiful, even poetic. First, let's have some data. These data are about the risk of banking fraud and come from an open data source. There are 776 cases and 25 variables. There are 23 predictor independent variables and 2 target, dependent or outcome variables. What each predictor variable measures is not important for this presentation, so they are simply labeled pred1 to pred23. The target variables are measures of risk. Out1 is numerical and out2 is categorical. We can tabulate out2 and see that the high risk category is relatively small, but nevertheless important to predict. The goal is to use the 23 predictor variables to build models that can accurately predict one or more of the target variables. But, as a matter of parsimony, are all these predictor variables really necessary? We need to explore the correlation structure of the variables and, if necessary, perform dimensionality reduction. The correlation coefficient measures the strength of relationship between 2 variables. Here is a matrix giving the correlation between each variable and all the other for all 23 predictor variables and the numerical target variable out1 in red. I've shaded in the diagonal where each variable is correlated with itself. The upper right of the matrix is mirrored in the lower left, with correlations equal to 1 down the diagonal, where each variable is perfectly correlated with itself. What we are looking for is low correlations between predictors and the target, and high correlations amongst the predictors. But there are too many numbers. Better to look at this graphically. Here, graphically, is the upper right of the correlation matrix. The size and color of the circles represent the value of the correlation coefficient between any 2 variables. Our main interest here is the correlation between predictors and the target variable, out1. Which ones are strong and which ones might be too weak? The graded color bar at the side shows the strength and direction of the relationship, with blue being positive and red being negative correlations. The middle is an area where correlations are small to 0, indicating negligible relationship between any 2 variables. A correlation of +1 at the top of the scale indicates a perfect positive match. A correlation of -1 at the bottom indicates a perfect inverse match, and 0 represents randomness. For parsimony, we would want to exclude at this stage any predictors that are random with the target. Pred 16 has the lowest correlation without 1, so we run a significance test. The null hypothesis is that the correlation is 0. P is less than 0.05, so we can safely reject the null hypothesis and say the relationship is small, but not 0 within the 95 confidence interval. Consequently, we can carry all the predictors forward to the next stage, as they have higher correlations than Pred 16. Now we turn our attention to the correlation between predictors. This correlation plot excludes any target variables. What we are looking for is evidence of high correlations between predictor variables that are likely to result in collinearity in building models. We can ignore the high correlations in the diagonal because they are just each predictor correlated with itself. But look at Pred 9, 10, and 11. They are highly correlated to each other, such that despite being different variables, they appear to be measuring the same thing. There are other such clusters as well. We need to analyze the structure of the correlation matrix to see how the variables group together. To begin the analysis, we need to inspect the eigenvalues. Where two or more predictor variables are highly correlated, they are likely to be measuring the same underlying dimension or component. Eigenvalues are calculated from the correlation matrix and express the amount of variance explained by a component. With 23 predictor variables, there are a maximum of 23 components, and the eigenvalues will sum to 23. The first handful of components have high eigenvalues and explain a high proportion of the variance, but this quickly declines to components that explain negligible amounts of variance. We can visualize this in a scree plot. The purpose of the eigenvalues is to help decide how many components we want from the principal components analysis. A rule of thumb is only to use eigenvalues greater than 1. That would suggest 7 components, which together account for 88% of the variance. But using PCA, we don't need to be too strict about this. Components 8 and 9 are not too far under 1 and well above 10, and would increase variance explained to 95%. So the choice is 7 or 9 components for the principal components analysis. I will explore 9. Here we have the loading matrix following principal components analysis. The 9 components have been rotated so they are orthogonal to each other in a 9-dimensional space. Only the rotation of RC1 to RC3 can be illustrated here. Each rotated component is a column. The loadings can be taken as the correlation each predictor has with a rotated component. As a rule of thumb, we are interested in component loadings greater than or equal to 0.7, and these are all shown here in red. Looking at RC9, only Pred 1 is strongly, negatively, correlated. Thus RC9 is predominantly the inverse of Pred 1. But RC4 has more than one predictor that strongly correlates with it. The same can be said for RC1 to RC7. That is, all those components with eigenvalues greater than 1 we saw earlier. Again, a graphic helps to visualize the loading matrix. Here we see how most rotated components are strongly associated with 2 or more predictors. At this point, we need to say something about the difference between exploratory factor analysis and principal components analysis. They can both be used for dimensionality reduction in the way shown here, and would broadly come to the same result. But the principal goal of factor analysis is to find latent variables, that is, a new variable such as RC4 constructed from pred1 to pred23, where each is weighted by their rotated component score. However, it can be difficult to know what these latent variables mean or how to deploy them in production. Principal components analysis allows us to identify that in RC4 there are 3 highly correlated variables, and that in the quest for parsimony we should choose just one. Here are some criteria that help in that choice. How strong is the correlation of each predictor with the target? What is the data quality of each predictor? Which predictor is easier and more cost-effective to measure? How intuitively understandable is each predictor? And how each predictor conforms to known theory or knowledge about the phenomenon being modeled. Based on these criteria, here is my final choice of predictors. Working from the right, RC9 is of course represented by pred1, and similarly RC8 is represented by pred16. For RC7 I've chosen pred4 rather than pred2. Similarly for RC5 I've chosen pred17 instead of pred15, and so on. In the end I have 9 predictors to take forward for modelling. The correlation matrix shows good correlations with the target variable, with much less internal correlation between predictors. There has been a logical and transparent process of whittling 23 predictors down to 9. Not all 9 will necessarily feature strongly in the predictive model to be created, but we have reduced the possibility of collinearity as required for sound regression model, and we have less complexity for exploring machine learning models. Here I've used the 9 predictors to create a decision tree to predict the categorical outcome. Each case ends up in a low, medium or high bin at the bottom of the tree. Accuracy is 94% and kappa is 0.88. A healthy result, though the confusion matrix will need to be inspected. But with 10 terminal nodes, some containing only a few cases, I'm worried about overfitting, so I'll explore pruning the tree. Here I've pruned the decision tree and I get a simpler, more intuitive tree. There is a small reduction in accuracy, but much less likely to be overfit, and therefore may perform better in production. The model uses only 4 predictors, and therefore in production only 4 attributes are required to classify new cases. This is a lot easier and cheaper than having to measure 23. When using other techniques such as random forests, artificial neural networks, or XGBoost, always look at the variable importance plot to see if there are unimportant predictors that can be dropped from the modelling in the quest for parsimony. This YouTube channel will feature a growing number of videos on quantitative and qualitative analysis and on machine learning. They are based on 25 years of master classes. Subscribe and look out for them.